Welcome back everyone. In this lecture, we will continue with the basic representation theory of Lie algebras. So, now we will actually define what we call homomorphism between two G modules or G representations. So, G module homomorphisms. So, let us start with two different G modules. So, let's say V and W be two G modules. Okay. Let us say they are given using these maps pi 1 and pi 2. So, pi 1 is a map from G to GL of V and then pi 2 is a map from G to GL of W. Okay. So, yeah, G module map or G module homomorphism, let us call it phi, is a C-linear map. Okay. A G module map or G module homomorphism is a C-linear map that satisfies the following condition. Following condition. So, whenever we take some element x in G and V in capital V, and if we compute the action of x on V and then apply this map phi, then this action should commute. So, this will give you exactly x of phi V for all x in G and V in V. Okay. So, whenever we take the action of G, that should commute with this phi. So, then we call this phi is actually G module homomorphism from V to V. So, in terms of these representations, we can see that, so this x goes to pi n of x is the first map and x goes to pi 2 of x is the second map. So, if we rewrite this star using this map, so this star means phi applied on phi 1 of x which is applied on V, which is same as phi 2 of x applied on phi of V. Okay. So, if we forget V, then it is same as saying that phi composition pi 1 of x is same as pi 2 of x composed phi, and this should be true for all x in G. Okay. It is not just only for one or two maps, it should be true for all x in G. Okay. So, that is the meaning of G module maps from V to V. So, now what is an isomorphism? Okay, sorry, this map from V to W. So, G module map, it is a G module homomorphism from V to W is C-linear map that satisfies this condition. So, now if we take set of all these G module maps from V to W, that is denoted by this home G V comma W. So, this is the set of all G module maps from V to W. So, when we take V equal to W, that means we are considering all the endomorphisms from V to W which are G module maps, that will be denoted by endomorphism of G V comma W. So, this is exactly same as home of G V comma V. So, when V equal to W, we use this new notation endomorphism of V. Okay. Later we will see that given two G modules V comma W, this home G V comma W also becomes G module using some natural action. But before that, let us define other terminologies. So, we say V and W are isomorphic. So, here is the isomorphism of G modules. So, we say V and W are isomorphic as G modules if there exists an isomorphism of there exists a bijective G module homomorphism. Okay, if you have a bijective G module homomorphism, it is easy to verify that the inverse map is also a G module homomorphism. Okay, because of that one can only demand we have a bijective G module map from V to W. So, if we have isomorphism between V and W, uh, then you can actually use this condition to rewrite that. But let us see actually what it means when we actually take V equal to W, because we want to actually classify all two-dimensional representations of this two-dimensional non-abelian Lie algebra and as well as two-dimensional abelian Lie algebra. Okay, so before actually doing that, let us actually see what this isomorphism means between actually same space. Okay. So, what we want to understand, sometimes we actually work with same n dimensional space, we will be looking at two different action of G on that. Okay. So, let us say G acts on capital V. So, V is just given to be n dimensional space. Okay. One can take it to be just Cn if you want. So, G acts on V. So, let us say via two different representations, pi 1 and pi 2. Okay. There are two different actions. So, we want to understand when these two actions are actually gives you same representation. Okay. That means we can define actually equivalence of representation by saying that they are just isomorphic to each other. Okay. So, that means we will be having a map from V to V such that, so this map should commute with both actions. So, that means phi of pi 1 of x applied on V should be equal to pi 2 of x applied on phi of V. So, this is exactly the condition that we have written here. Okay. So, now because we are dealing with the same space or same n dimensional space, so this can be rewritten as follows. So, this gives you exactly phi composition pi 1 of x equal to pi 2 of x composition phi. So, now what is pi 1? Pi 1 is a map from G to actually GL of V. Okay. Note that V has n dimensional. So, basically pi 1 of x is n by n matrix. So, this is n by n matrix, this is n by n matrix, this is n by n matrix, this is n by n matrix. So, that means I can actually like, because this phi is given to be bijective G module map. So, that means it is invertible C linear map. So, this is invertible C linear map. So, that means I will be able to actually invert it and then rewrite this equation as follows. So, this equation can be written as phi composition pi 1 of x composition phi inverse will be exactly equal to phi 2 of x, and this should be true for all x in G. Okay. So, pi 1 and pi 2 being isomorphic, pi 1 isomorphic to pi 2 as a G module can be rewritten as there exists one single operator phi, invertible operator, such that whenever you take the conjugate of pi 1 of x with respect to that operator pi, so then we get pi 2 of x for all x in G. Okay. Sometimes this operator will be called intertwining operator in the literature, okay, because of this reasons. Okay. So, let us see one example, okay, to convince you that what this means. Okay. So, do not be afraid that we are taking the same space, okay, but we need to consider different actions. Okay. We need to compare various different actions of G on the same space. Okay. So, as long as vector space structure is considered, any 5 dimensional, okay, n dimensional space will be isomorphic to like another n dimensional space as a vector space, but as G representation they may not be isomorphic. So, that is what we want to try to understand. If they are isomorphic, then we are saying that that means this very strong condition should be satisfied. Okay. So, let us look at some example and then try to understand this. So, let us say we take this G2, so which is the span of let us say S comma T, where S is nothing but E11 and T is nothing but E12. So, in particularly if I take the bracket ST, we get back T. Okay. So, this is 2 dimensional non-abelian Lie algebra, and any 2 dimensional non-abelian algebra will be isomorphic to this G2. Okay. So, here is the first example of this representation G2. For example, G2 acts on C2 in 2 different ways. Okay. G2 acts on C2. So, via like let us say pi 1. So, what is pi 1? So, pi 1 is we can actually just tell how S and T acts, then we can actually extend that to any element of G2. So, I am going to tell you how S acts. So, S acts as 1 0 0 0 and then T acts as 0 1 0 0. So, this is the natural representation of G2 acting on C2. Now, here is another representation which is given as follows. So, we can take this action of S to be just 0 0 0 1 and then the action of T to be 0 0 minus 1 0. Okay. So, even though I have written actually 2 different action, it is the second action is indeed obtained from the first action by conjugating the following G. Okay. So, I will leave it to you to verify that if we take this phi to be this 0 1 minus 1 0, so then these two actions are actually conjugate. So, that means, so the even though they are two different actions, okay, but they are isomorphic as G2 action. So, pi 1 isomorphic to pi 2 as G representations. Okay. So, now once we have defined this isomorphism of representations, so then here is biggest problem in representation theory that can be stated. So, the biggest problem is that given G, okay, classify all, okay, G representations, of course, up to isomorphisms. Because we understand isomorphic representations, so they share everything in common. Okay. So, that is why we want to actually classify all G representations up to this isomorphism class. So, basically we take this set of all representations, okay, call it the script A. So, this is so usual, okay, the usual notation is the rep G. So, that is the category. So, let us use that notation. So, rep G is the set of all G representations. So, then one can define this equivalence relation. So, we define this relation on this rep G. So, given by, so we say that two representations are equivalent if and only if they are isomorphic. Okay. So, now what we are interested in? We are interested in classifying all this representation of G up to actually isomorphism. That means, we want to find, okay, representatives of these classes that are there in representations of G. So, usually what is the meaning of this? So, that means you try to find some parameterizing set, okay, and then we have the one to one correspondence between that parameterizing set to this rep G modulo tilde. So, that is the ultimate aim, okay. And given that element from that parameterizing set, we should know how to actually create this representation that you have inside this rep G modulo tilde. Okay. So, we will see towards that, okay, uh, many examples. Okay. So, first I will begin with for example, two dimensional abelian Lie algebra. So, we begin with two dimensional abelian Lie algebra and classify all two dimensional representation of the, okay, let us call this is G. Okay. So, maybe like let us use this better notation. So, let me call it A2. So, A2, what I mean by it is a two dimensional abelian Lie algebra. So, more generally let us use AN for the n dimensional abelian Lie algebra. Okay. So, what we want to do now, we want to actually classify all, okay, classify all two dimensional representations of this A2. Okay, that is a problem first I will be working. So, we will do the similar classification for again non-abelian two dimensional Lie algebra. Okay. So, that actually at least gives you some understanding of what we are dealing with. Okay. Before that, I want to make one important warning. Okay. We are actually now dealing with Lie algebra representations. So, one can also define representations for associative algebras. Okay. So, let us recall what is the definition of associative algebra, because later I will be actually defining what is called the universal enveloping algebra associated with the Lie algebra. So, let us first recall the definition of associative algebra for the purpose. So, what is an associative algebra? So, we have already seen many examples. Okay. So, the set of all n by n matrices is nothing but associative algebra. And then if it, there are many very good examples of associative subalgebra of that set of all matrices. For example, if we take the set of all diagonal matrices, okay, that will form a actually associative subalgebra of that. So, so what is an associative algebra? So, to begin with, the associative algebra, it is a vector space. Okay. So, let us call this A is associative algebra. So, A is a vector space over C to begin with. So, that means it has this vector space structure that is given by A plus and this scalar multiplication dot. Okay. So, this is the addition that is there in the vector space, and this is the scalar multiplication. So, that is there in this vector space. Okay. So, this is the vector space structure. So, not only it is just a vector space, it also has additionally multiplication. So, that makes it as a ring. Okay. So, we also have addition and then multiplication. So, that makes it a ring. Okay. So, this addition of this ring structure and the vector space structure, they are same. Okay. Here are the important points. Okay. The addition of the vector space structure is same as addition of the ring structure. So, that is the first compatibility condition between these two structures, that is the most important thing. So, we also assume that all our associative algebras are unital. So, that means we have multiplication identity. Okay. We denote that by 1A. So, that is called multiplication identity. and we assume that this is there in capital A. So, these are all the conditions. This is first, second and third. And the fourth condition, so we need to have some compatibility between these two structure. This is the first compatibility. So, here is the second compatibility. So, whenever we take scalars lambda and then elements a b in capital A, when we compute the product, lambda a b should be same as a times lambda b, which is same as lambda a times b, and this should be true for all lambda inside C and a b inside capital A. First of all, what is lambda? Okay, so because scalar multiplication is well defined, so lambda a b is well defined, so this is fine, no issue. Now, more than this, we have this another important compatibility. So, we have a map, natural map from C to capital A, that is given by lambda goes to lambda times 1a. Okay. And if we call this map is pi, then the image of pi, so that must be sitting inside the center of A. Okay. So, that means all the scalars must commute with all the elements of capital A. Okay. So, this is sitting inside the center of capital A. So, we often identify lambda with lambda 1a. So, we often identify with lambda with lambda 1a. Okay. So, most of the time we will be working with nice algebra that contains C. So, that is why we will be able to do this. Otherwise, more generally associative algebra over C must satisfy only this condition, that there is a map from, this is a ring homomorphism. Okay. So, this is a ring or algebra homomorphism also you can say. So, that means C linear map plus ring homomorphism. So, now in our examples, most of the time the complex number will be sitting inside the algebra. So, we can identify lambda with lambda 1a, there is no issue. Okay. So, the vector space addition and ring addition must be same. So, that is another condition. So, there are two structures like vector space structure and the ring structure. So, both structure must have some compatibility to work with that algebra. Okay. For example, if we take set of all matrices that has matrix multiplication, matrix addition and scalar multiplication of matrices. So, using that it becomes actually associative algebra over C. So, we are only going to deal with associative algebras over C. So, now from this ring theory or algebra, associative algebra theory, we can also study modules for that. Okay. For example, if I start with A, that is just associative subalgebra of M1 of C. So, then for this one can define A modules. So, basically they satisfy the following condition. For example, if we take A B and then apply it on V, then that will be exactly A of B V. Okay. This is true for all A B in capital A and V in capital V. Okay. Let us say V is A module, then we have this. So, now using this, if we think this A as Lie algebra, so suppose if we consider this Lie algebra structure, so this is associative algebra, associative subalgebra, and from this we are considering this Lie algebra. So, where the product, the Lie product is given by AB minus BA. So, now if we take this Lie algebra, then the same module capital V, which is associative algebra module, also can be treated as this Lie algebra module. Okay. That is because whenever we take this bracket AB acting on V, then you can easily see that this is nothing but AB minus BA acting on V. Now, using this condition star, we can see that this is same as A of B of V minus B of A of V, and this is true for all AB inside V, AB inside this capital A and V in capital V. So, that means this capital V can be regarded as this Lie algebra module, okay, that is not a problem. But the converse is not true usually, okay. Most of the time the converse is not true, okay. So, the warning is that the converse of this is not true. For example, we can have many GLN modules, okay. So, we can have examples in GLN case itself, okay. So, many GLN modules will not be modules for the matrix algebra Mn of C, okay. So, that is a very important remark. So, we should not get confused with two different representation theory. So, there is a representation theory of associative algebras and there is a representation theory of Lie algebras. Sometimes one can go from this representation theory of associative algebras to Lie algebras, but conversely we can't actually just generalize or sorry just go from any Lie algebra the bracket A to A, okay. But we will later make this connection between the representation theory of associative algebras and representation of Lie algebras using what is called the universal enveloping algebra, okay. So, there is a natural associative algebra that we define for any given G. So, that will be called the universal enveloping algebra, and we will see later that there is a very close relationship between the representation theory of Lie algebras and its universal enveloping algebras, okay. So, that is the only connection that we have, okay. So, let us get back to actually our goal. So, if we actually take this two dimensional representation, so let me just write down what that means, okay. So, we want to consider this A2. So, let us say which is the span of x comma y where the x comma y commutes, okay. So, if we are interested in defining the representations, okay, let us say what that means, okay. Let us say you have a representation from A to some GL of V. So, that means this x is mapped to some capital X and this y is mapped to some capital Y. But the important thing is this capital X and capital Y must commute, okay. Suppose if you have one action, okay, let us call it, so let us label it pi 1 as before. If you have one representation which is pi 1 and then another representation, okay, again from A to 2 GL of V. So, let us say we are only interested in classifying two dimensional representation, okay, two dimensional representation of A2. So, then this x is mapped to x dash and then let us say y is mapped to y dash, okay. So, we already seen that what is the meaning of pi 1 being equivalent to pi 2. So, pi 1 isomorphic to pi 2 as A2 modules. So, that is same as saying that, so these two representations are isomorphic. So, that means there exist G. So, note that this x dash and y dash also must commute because they are image of x and y. So, there exists G in GL2 such that this G x g inverse must be x dash and g y g inverse must be y dash. So, that is the meaning of these two representations being equivalent. Okay, this is same as saying that the phi composition pi 1 composition pi inverse is same as pi 2. So, this is the condition and this is true for each x. So, we are actually using the basis element set. Okay. So, if we use the basis element, that is good enough for us. So, now this means the classification of two dimensional representations of this abelian D algebra boils down to the following problem. So, I can take this set X, which is the matrices xy, which comes from M2 of C cross M2 of C, such that first of all this matrix commutes. Okay. So, now we define sub-equivalence relation on this S such that satisfying these two conditions, whenever x and y related to x dash y dash, if and only if there exists G in GL2 such that G x G inverse equal to x dash and G y G inverse is equal to y dash. So, this condition should be satisfied. Okay. So, now if you think about it, given any matrix can be transformed to up to conjugation to its Jordan form, okay, because we are working over complex numbers. Okay. So, because we are actually simultaneously conjugating both x and y. So, now we can choose the conjugation of y so that y becomes Jordan form. Okay. So, without loss of generality, one can assume y is in its Jordan form. So, now we are dealing with general 2 by 2 matrices. So, what are all the possible Jordan forms? Okay. So, the possible Jordan forms for y. So, it can be actually, so let us deal in terms of the eigenvalues. So, it can have two distinct eigenvalues, it can have same single eigenvalue. If it has two distinct eigenvalues, then that would immediately implies that the matrix must be diagonalizable. So, then the Jordan form will be just diagonal matrix A 0 0 B. Okay. So, A 0 0 B, if it has two distinct eigenvalues. Okay. So, if it has two distinct eigenvalues, then that implies it is diagonalizable, since it becomes diagonalizable, because the corresponding eigenvectors must be linearly independent, that if you form a basis out of it, then you will get this diagonal matrix. So, now if you take if it has single eigenvalue with the multiplicity 2, so both cases can appear, it can be diagonalizable and it may not be diagonalizable. If it is diagonalizable, then it should be of the form A 0 0 A. If it is not diagonalizable, then it should be of the form A 1 0 A. So, this is the case, okay, where single eigenvalue with the multiplicity 2, and in this case this is diagonalizable, and in this case not diagonalizable. So, we need to consider all these cases and then see what happens. Okay, let me just do only one case and then I will leave it to you to actually check other cases. So, basically we got some parameterizing set. Okay, basically we need to see what are all the equivalence classes in this S modulo tilde. We need to find representative of that. That is our goal. So, as we noticed, we can actually assume that y is in the Jordan canonical form. So, without loss of generality, we will be assuming that in the calculations. So, let us consider the cases. So, the following are the possible Jordan canonical forms for the 2 by 2 matrices. So, Jordan forms of 2 by 2 matrices. So, we may have actually two distinct eigenvalues. In that case, it will be diagonalizable. So, it will be actually similar to the diagonal matrix A0 0 B. So, this is the first case A0 0 B. So, this is diagonalizable. So, we may have actually diagonalizable, but repeated eigenvalues. So, in that case we will have scalar matrix A0 0 A. This is again distinct eigenvalues in the first case. In the second case, repeated eigenvalues, but diagonalizable. The third case, not diagonalizable, but it is forced to have repeated eigenvalues. So, not diagonalizable. So, these are all the three cases that we need to actually consider. So, let us consider one by one. So, as before, like the representations that are associated with matrices x y isomorphic to the matrices x dash y dash, if and only if, note that we define this relation x dash x comma y related to x dash y dash if and only if there exists invertible matrix G in GL2 of C such that G x G inverse is given by x dash and G y G inverse is given by y dash. So, now let us assume the case 1. So, the case 1 is y is diagonalizable. So, when y is diagonalizable because it has distinct roots. Okay. So, the case 1 is y has distinct eigenvalues, that is y has distinct eigenvalues. So, let's take that as first case, and this immediately implies y is diagonalizable. Okay. So, now x and y they commute. Okay. The property of the pair x y is x y equal to y x and x dash y dash equal to y dash x dash. So, since x and y commute, so the eigen vector of y should be mapped to that. Okay. So, let us say like V1 and V2, they are the eigenvectors of y corresponding to the distinct eigenvalues, let us say A and B. Okay. So, now it is easy to see that when you take x V1, it has to be element of C1. CV1. Similarly, x V2 should be element of CV2. So, it is simple calculation because if we take x V1 and then apply y, then we get x y V1. So, that means you get x. So, y V1 is just a V1. So, you get a V1 here. So, this gives you a x V1. So, that means x V1 becomes again, if it is non-zero, eigenvector for the corresponding to the eigenvalue A. but that is actually one dimensional space. So, that forces that xv1 is element of this one dimensional space cv1. Similarly, we get this xv2 inside cv2. So, that means x must be diagonalizable. So, this implies x is diagonalizable. So, since x and y both commute, so they can be actually diagonalized simultaneously. So, that means there exists G in GL2 of C such that G x G inverse, that is of the diagonal form. So, this is some C0 0 D where C D can be complex numbers, and then G y G inverse, that must be A 0 0 B, but A should be not equal to B. Okay. So, in particularly we get that this x y related to these two matrices C 0 0 D comma A 0 0 B. So, all two dimensional representations of this abelian Lie algebra. So, that will be actually in this case will be parameterized by these tuples. So, now if we take this case 2 where y is diagonalizable plus repeated eigenvalues, So, then we can actually say that so y will be similar to A 0 0 A. Okay. So, where A is the eigenvalue. So, this A is the eigenvalue of y. So, now note that so A times identity, this is scalar matrix A times identity. So, that commutes with any matrix. Okay. So, now if we take this x and y tuple, then it is naturally related to. So, we can actually make x into the Jordan form. So, you choose G such that G x G inverse becomes Jordan form. Okay. So, then if we assume that without loss of generality y is of this form A times scalar. So, this is A times this scalar matrix A times identity. So, this is something we can assume without loss of generality. So, then you can see that this choice of this G in GL2 of C gives you that this Jordan form of that is similar to capital X. So, then for that same G, so we will have G y G inverse equal to y, because y is A times identity. Okay. And this is true for any G in GL2 of C. So, that is why, so this pair x comma y will be related to x, the Jordan form corresponding to x and this A times identity. Okay. So, in this case the parametrizing tuples will be this x Jordan form comma A times identity. So, we left with only the last case. So, that is y is non-diagonalizable. If y is non-diagonalizable, then y will be of the form actually, like let us say by conjugation we can just without loss of generality assume that y is of the form A1 0 A, where A is coming from some complex numbers and A is the eigenvalue of that y. So, now in this case, so I will leave it to you to check. So, whenever x and y commutes, then x also has this particular form. Okay. Since x and y commutes, if you write x in the form of some C, D, E, F, then you can see that x also will take the form something like this B C 0 B. Okay. So, this is just a simple computation. So, then one can actually see that this x and y will be related to this type of tuples. Okay. So, in particularly this actually forms this actually gives the parametrizing tuple. So, this way actually one actually classifies all possible two-dimensional representations of abelian two-dimensional abelian algebra. Okay, I will stop here. We will actually continue with some more examples in the next lecture. Thank you.